Hello and welcome to Understanding Design in the Construction Industry. My name is Ian Taylor. I am a project manager for Turner & Townsend here in the city of New York, and I'll be happy to introduce to you the following module. The island of Manhattan is one of the most iconic urban landscapes you can find in North America. A more humbling notion lies within the fact that the backdrop that you are observing here was created by a very small, tight-knit group of professionals. That tight-knit group of professionals built this urban landscape on top of what was left behind by their predecessors. Every aspect of the built environment encompasses a vision set forth by design professionals. The vision eventually makes its way into a rudimentary design and becomes further and further developed until it is finally prepared to be brought to market. As a construction professional, it is important to understand the construction design process and how it relates to cost management and estimating project costs. Depicted here, you can observe what we term the full spectrum of construction design. This shows you the full life cycle of design from start to end. It is worth noting that design changes can be made at any period along the design spectrum. Here, in the middle of the design spectrum, you will see that there is a clear demarcation of contract award, which brings us from the pre-construction and design phase to the construction phase. This is the point all design changes will be qualified as change orders, which will be covered more thoroughly at a later topic. Here you will see an overview of the construction design stages. Typically, you will begin with an order of magnitude or a conceptual design, which will bring the vision of the design consultants to life. That will be later developed into a more robust schematic design, further developed into a design development document, and then finally coming forth with the full construction design. So we will begin with the order of magnitude estimate. This is typically done as the conceptual estimate, or the first stage of design within the project. This is typically based on a square foot or unit cost and has a low degree of accuracy, typically within a 25 to 50% margin of error. This is oftentimes referred to as the rough order of magnitude or the ROM estimate. With regard to estimate accuracy, it's important to note the concept of contingency and making sure that enough of it is built into your estimate early. We will cover more on the topic of contingency at a later module. Depicted here, you will see an example of an order of magnitude level design. As you can see on the plan, there's little detail outside of the building envelope and core features such as elevators, stairwells, and utility closets. This provides the footprint or baseline to which the designer can further develop his vision. An example of an order of magnitude estimate would be based on the notion that company XYZ wants to build a building of 20,000 square feet. They want to keep to a budget of $300 a square foot. Thus, you can perform a simple calculation of $300 times 20,000 square feet for a grand total budget of $6 million. Next, we're going to speak about the schematic design phase. At this point, the building will be laid out and the interior program will be established. You can expect the accuracy of your estimate to be within a 15 to 20% margin of error. And this includes an idea of the facade finish, the structural system, whether that will be steel, concrete, or CMU block, and a general layout of the typical floors will be shown. Architects will typically at this stage have the guidelines that they need to be able to move forward to the next stage. So as you can see here, we have an idea of what is envisioned within the space. There are areas designated for workspace, conferencing, restrooms, as well as an interior stairwell. Individual plans for each specific work stream have not yet fully been identified. This would include furniture, ceiling, floor, and wall finishes. From an estimating standpoint, you will need to make assumptions on what will be included in the space. As you can see by our example, we have created general buckets for each individual work stream. Architectural systems, structural systems, mechanical, electrical, plumbing, and fire alarm systems will all need to be accounted for. The next stage of design we're going to discuss is design development. At this point, the architect has further developed the guidelines for the project. The accuracy of the estimate can be expected to be within a 10% margin of error, and it includes selection of departments and establishment of functional areas, such as pantries, bathrooms, conference rooms, workstations, and private offices. At this stage, you'll begin to see individual drawings for each specific workstream. This can include reflected ceiling plans, finish plans, furniture plans, HVAC, electrical, and plumbing plans. For illustration purposes, we have selected to show you a standard floor plan. Here you will find that bathrooms have been fully identified, breakout areas within the workspace have been quantified, as well as partitions existing for storage, conferencing, and coat closets. You can even see that the beginning of the stair design has begun to take place. As you can see in our example, the details of the estimate have become more defined. We have selected to analyze specifically the architectural items within the design development level plans. We can now understand the intent as it pertains to walls, flooring, ceiling, doors, and glass partitions. You can even begin to associate quantities to each of these individual items at this level of design. Next, we're going to speak about the construction design level. At this point, all the specifications and drawings for the construction project will have been completed. We can expect the accuracy of our estimate to be within a 5% margin of error, and details will be fully established for flooring systems, ceiling systems, furniture, MEP systems, and the subcontractor will be able to develop shop drawings based on these documents. The construction design is the most defined set of drawings that the design consultants will produce. Each of the individual work streams that were introduced in the design development phase will now be fully designed and prepared for final pricing. Constructors will use these documents to produce engineered shop drawings to ensure constructability and that the design intent is met. As you can see by our example, we have fully identified the following areas: conferencing spaces, breakout areas, the pantry area, the exact stair locations, your elevator lobbies and finishes, and even your wall and ceiling types. Depicted here is a typical wall detail that you will find within a construction design level document. Here you will find gypsum board type, steel stud type, insulation type, and steel track type. These details will be rolled up into your detailed CD level estimate. You will see in our example that we have further drilled down in the architectural workstream specifically into walls. Here you will see all the components for this specific wall type are individually priced, and thus create the most detailed estimate to be performed pre-bid. Now you can see how this differs greatly from the order of magnitude estimate and how the level of design will dictate how detailed your estimate will become. So next we're going to delve into a case study on 601 Lexington Avenue, which currently stands today in Midtown Manhattan. It is a proud 59 stories tall. The structural engineer on the project was William LeMessurier, who we'll speak more about in a little bit. Construction took place from 1974 to 1976, and it cost roughly $195 million to complete, which adjusts for $761 million in 2016. The most interesting fact about this building is that it contained a major design flaw. Diane Hartley, an undergraduate student at the time, was preparing her thesis on the building and called the structural engineer to explain her analysis yielded the following conclusion. Perpendicular winds were accounted for and did not present a threat. However, quartering winds, or those that hit the building at its corners, were not accounted for and pose a very serious threat to the structure. She further concluded that winds over 50 miles per hour at the correct angle would cause a cascading failure of the building. Weather data also suggested that there was a possibility that winds of this nature could occur as often as 1 in every 16 years on the island of Manhattan. What's interesting about the design of the building is the chevron systems that were placed within the structure to ensure its stability. As you can see, the major columns were placed in the center of the building, not on the edges, to accommodate the location of the church. So large structural steel beams had to be created, spanning 8 floors within the building in order to support the structure. Now, it's not natural for beams of this size to be flown in one piece. It has to actually be broken down into different sections for constructability purposes. So what the subcontractor had done at the time was split the sections of the chevrons spanning into 2 floors. What the subcontractor had decided to do, and by using all of the proper channels, was use a bolting method to create a bond between the structural members. That include placing a plate on either side and then bolting through. The decision to go to a bolted system rather than a full penetration weld system was the death knell for the chevron design for the building. Had the full penetration welds been performed, the wind threat may not have been so high. As a result, the entire building had to be re-welded without any knowledge of any of its occupants or for the greater population of Manhattan. All of these welds were completed after hours and came to a total cost of $8 million in 1978, which adjusts for roughly $30 million in 2016. I wanted to illustrate this point as it relates to design costs as the construction project continues. As you can see here, the cost of implementing design changes beyond the design phase can have significant cost impacts to your project. Finally, I'd like to offer you some tips in understanding construction design. It's very important that you read all the notes and details within the drawings. It's important that you generate RFIs or requests for information when the details are not clear. It's also very important that you maintain an RFI log so you can understand which items are open and which items need to be followed up with. You can also utilize your professional network if you happen to get stuck on a particular topic. Finally, please make sure to apply contingency based on the level of detail you see within the design pack. An example would be 20% contingency to your overall price. We hope you enjoyed this module. Thank you very much for joining us.